All right, so we're doing day 2 of limits. And we were going to start off, if you were in class, we played Quizlet, but we did talk about some things graphically, which is what the Quizlet was on, so we'll discuss that. Then we're going to look at some properties of some limits and some strategies that we can have for some of those limits that we can't just do a nice direct substitution. If there's a way maybe to do it without a table or a graph, we'd love to be able to do that. All right, so we're going to look first at a kind of a recap from yesterday and looking at a graph and trying to determine the limit. So when we look at some weird graphs, sometimes this is a little bit tricky for people to get their head wrapped around. So I'm going to kind of recap it, and then we would play a Quizlet game. So I'm going to go ahead and I'm going to call this first graph f of x, and these first questions are on that graph, and then this one is g of x, and so those questions are on that graph. So looking at this first one, it says find the limit of f of x, so that's this graph here, as x approaches 4. So what you're doing here is you're looking at your x-axis and finding where it's 4, that's right here. But you're looking at the function when x is 4, so now you track it to wherever it hits the function, that's right here. So you're looking at this spot right here on the graph. And then what you do is you sort of come in from the right side, and you come in towards the left from the left side here, and you're tracking that function with your fingers or whatever it is, and you're evaluating what the y value is approaching. Remember what the y value is approaching as you get to that spot. Now, this is a nice continuous function, so there's nothing funky going on. We would just say, hey, it looks like my y value is approaching a -4 right there. So that limit would equal -4. All right, let's try again. This time, I'm going to have my x approach 5. So x is 5 right here, which happens to also land right on the graph. And so as you approach that position from both directions, it looks like that your y value is going to get closer and closer to 0. So we'd put a 0 there. Continuous functions are pretty straightforward. But now I'm going to mix it up a little bit. I'm going to change our graph a little bit, and I'm going to put a hole at 5 and see how that changes it. So let's pretend this was a parabola, but there was a hole in the graph right here at 5. Instead of it being just nice and continuous, it would be considered discontinuous. Now when you do this, and you come in from the left and from the right, what would you say that the limit is now? I'm hoping you're saying it's still 0. That hole doesn't mean anything. It doesn't matter that it's undefined at that spot. It's still about what it's approaching. And so that hole plays no part in the limit being undefined or something like that. We would still say it has a limit of 0. All right, so that's one quirky thing. The other one are these graphs that are kind of like just break off and have this jump or something going on. Okay, so let's see the different options we have on this one. So on this first one, x is approaching 3. So at x equals 3, that happens right here. So you go to the function at that spot, and it's right here. Now, as you come in from the left and from the right, your y value is approaching, and actually it ends up equaling 1. So you would say that the limit is equal to 1. Now, these are those new notations we have. What if x is approaching 3? Do you remember what this minus sign at the end means? It's not a -3. It's a x approaches 3 from the left. Okay, so if you look at that spot again right here, as you come in from the left, well, it was still 1. As I came in from the right, it would have been 1 also. Okay, let's change up where we're approaching. On this example, it says x approaches 1. Now that's a little bit different because 1 is the exact spot where something funny is going on with the graph. It's jumping here. And so the problem I would have here is as I approach from the left, it looks like it's approaching a -1. But as I approach from the right, the y value is approaching 1, and they're approaching different values. That is not okay. That's our situation where we would say no limit. And then remember, we always give a reason, and we're going to say that it approaches different values. Now, if we have that scenario, that's when we start introducing this idea of just doing one-sided limits. Well, what if I was only coming in from the right side? Then I can say there's a limit. If I'm coming in towards 1 from the right, the y value is approaching a 1. And that's okay, as long as we dictate it to be a one-sided limit. All right, and just because the notation on this looks crazy, I threw this one in here. What if x is approaching -1 from the left? Looks crazy. Approaching -1 from the left. All right. Oh, look, -1 is the exact spot where it jumps here. So what do you think we should write here? We should write 1, because it's a one-sided limit. I don't really care that it jumps in the other direction, it's going to something different, because I've made it a one-sided limit, then it's okay to evaluate. Okay, just kind of a recap of the graphs. All right, so we're going to move into looking at some ways, some strategies we have of evaluating limits without having to get into doing tables and graphs. So polynomials, like parabolas, cubics, quartics, kind of like that bounce cut packet thing that we might have done in college algebra. Since polynomials are continuous functions, you're always going to do direct substitution. You always want to try direct substitution first to see if it's going to work. Well, this is just a parabola, and there is nothing fancy about it. It's just a parabola. And so I can do my direct substitution. I'm going to put a -1 in. All right, so you have a -1. I'm going to change colors up here, sorry, so you can see it a little bit better. -1 squared plus a -1 minus a 6. And so that's just going to be a 1 minus a 1, which is 0, minus a 6. So the limit on this one is -6. Best case scenario, direct substitution. Now, what we're really spending our time today on are the discontinuous functions, where you can't just do direct substitution, and maybe there's some sort of algebraic way of handling those. So here's what our strategies are. If it's something that looks like it might be able to factor and reduce, that would be a great strategy to kind of clean up the function. Or maybe you've got some fractions, you'd get a common denominator to try to combine them together. That would happen on any time you're given rationals. If you're given radicals, we're used to the concept of rationalizing the denominator, which we can still do, but sometimes it's the numerator that has the radical. Well, we can also rationalize the numerator. It isn't really about getting it to look cleaner. It's really about being able to do some reducing. And if you can do some algebraic tricks to get it to reduce, that's what we want to be able to do. All right, and then another type of discontinuous function would be that piecewise function that sort of has some sort of a jump in it somewhere. It's pieces of different functions put together. In that scenario, you want to check your left-sided limit and your right-sided limit on those. All right, if none of these work, okay, then we might have to go back to the graph or the table or something. So let's start off. I got one here. It's a rational. You can see that it's in fraction form. And I had said earlier on rationals, maybe you try to get common denominators or something. Well, that's not really what's going on here. I do see that there's a polynomial that might be able to factor, and then we can maybe reduce. But the number one method should always be just try to do direct substitution. Look, x is approaching 1. Let's plug 1 in and see what happens. If I plug 1 in the denominator, I'm going to get a 3. If I plug 1 in the numerator, 1 squared is 1 plus 1 plus 2. Okay, so that's going to be a 4. So then that is totally fine. The limit is 4/3. Now, just so that you understand what's going on with this function graphically, it is irrational, so something is happening here at -2. Because if I had put -2 in, that would have been a 0 in the denominator. Well, this is actually the graph of it. There's an asymptote going on at -2. And that would be problematic if that was the spot I was approaching. So don't automatically assume this is a no limit, unbounded behavior or anything like that from yesterday, because you have to first identify where you're approaching. And I'm approaching x equals 1, which is about right here, which is a little bit above the 1. So I like 4/3 for an answer on that one. Okay, let's try another one here. All right, down here, x is approaching -3, and that is problematic. That is going to become what I'd like to think is a no limit, but I don't really know why. So instead of just jumping into the assumption that it's a no limit because direct substitution doesn't work, I want to try to clean this up and see if I can reduce. So in my numerator, that is going to factor for me. Factors of 6 that have a difference of 1, that's going to be a 3 and a 2. I'm going to want a +3 and a -2, and that's all over an x plus 3. Oh, look there. Those are going to cancel out for us. So since those cancel out, I'm really looking at the limit as x approaches -3 of x minus 2. Now I can do the direct substitution. So the limit, if I put in that -3 minus 2, I'd have a limit of -5 there. Now, what's actually going on graphically, so that you understand how this plays out, is if you were to put this in your calculator, put this whole thing in your calculator, it would really look like this right here. It's going to just look like a line. And you're going to think, what? That should be fancier than a line, but it reduces to a line. And what's happening with these is this is creating a hole in the graph. So you don't see it on your graphing calculator, but it would be a line that has a hole in it at -3. And remember that the hole does not mean there's not a limit. We learned that on those graphs earlier. There can still be a limit even if there's a hole in the graph. Okay, let's try one more here, a little fancier. Always looking to do direct substitution first. So if I put a 1 here, I would have a 1 minus a 1 plus a 1 minus a 1. That's going to end up a 0. So that is problematic. So I can't do direct substitution. So I'm going to try that factoring game. This is a nice 4-term polynomial that we would try to do factor by grouping with. Pull out a GCF here of x squared. I can't pull anything out of the second one, but remember, you got to pull out some sort of a placeholder. I'm going to pull out a 1 on it. So now what I have is x squared plus 1 and an x minus 1. And I like that because I see there's an x minus 1 and an x minus 1 here. So those would actually end up canceling out. That x minus 1 and that x minus 1 would cancel out. So what I'm left with here, remember though, this is still in your denominator, so it's a limit as x approaches 1 of 1, since that canceled out, over x squared plus 1. And now we try to do that direct substitution again. If you put your 1 in here, 1 squared, that's 1 plus 1, that's 2. So your limit is going to end up being 1/2. Okay, let's try this fraction. This is a little bit trickier of a fraction than the previous slide. It's what we call a complex fraction. That is when you have fractions caught up inside of fractions. Now, sometimes you even have a fraction in the denominator. In this case, it's not, but I sort of treat it like it is. So what we do is we try to condense the numerator here into a single fraction. And then if I had multiple things here, I would try to condense it so that I'd have one fraction on top of one fraction. So to get a common denominator so that I can subtract these, I have to combine, or I have to look and see what would the common denominator be between these two denominators. Don't forget that this 3 is not the same as this 3. This plus sign ties this together as its own thing. It's an x plus 3. And then I got to take it times a 3. So my common denominator will be the x plus 3 and the 3. What I'm missing here is on the left side, I'm missing the times 3 that needs to be there. So I'm going to take the top and the bottom times 3. On the right side, what I'm missing is the x plus 3. So I'm going to top and bottom times x plus 3. So that's going to turn into, common denominator is an x plus 3 times a 3. My numerator is going to be, and I just do this all in one shot. Some people like to still have this in two parts, but we've been doing this since Algebra 2. So this is my common denominator, and my numerator is going to be a 3. And then over here, don't forget that this minus sign has to go to everything. So it's like there's a -1 that distributes through there. So I'm going to end up with a 3, and then it's going to be a -1x minus a 3. And this is all over this x right here. But I'm going to go ahead and call it x over 1 and turn it into a fraction. All right, next step, go ahead and clean it up. So I'm kind of moving to the right here as I do this. In my numerator, I have a +3 and a -3. Those are going to cancel out. So then I'm left with a -x over 3x plus 3. Nothing else is going to cancel there. Over x over 1. And now this is the place where instead of dividing by a fraction, we pop it up and multiply by the reciprocal. So that's why I kind of wanted to write that as a fraction so that I could multiply by the reciprocal. And now I see one more thing that can reduce. This x and this x can reduce. Now that negative is still sitting there. So here's where I think I'm at. I've got the limit as x approaches 0 of, I have a -1 over a 3x plus 3. And now my goal is, by doing a little bit of reducing, I'm hoping now that I'm going to be able to do this direct substitution. Now I can plug a 0 in here. So that's going to be a 3 times a 3. So it looks like my limit is going to end up being a -1 over a 9. All right, so another strategy. All right, still got a fraction here, but this time I've got a radical in it. So the thing with this, as always, we're trying direct substitution, but I think you can pretty quickly see we're not going to be able to plug 0 in because it creates a 0 in our denominator. And so what we're going to do is, instead of rationalizing our denominator, like we're kind of familiar doing, we're going to rationalize the numerator. And it's just a way of sort of rearranging the expression. Now, this is the thing where you do the conjugate. So I'm looking at this. So to rationalize it, I have to multiply by the exact same thing, but this sign right here has to change. Not this one, just the middle one. So I'm going to end up with a square root of 25 plus x. And instead of a -5, I'm going to have a +5. And then I also do this in the denominator. Okay, now the idea is that in the numerator, when you multiply by the conjugate, some stuff is supposed to cancel out nicely. So right here, when you take the first times the first here, when I'm foiling this together, since they're both radicals and they're the same thing, that square root, I'm really taking it and I'm squaring it, which is going to get rid of the square root. So I end up with just a 25 plus x. And then again, the conjugate thing, when I take this times a positive 5 and this times a negative 5, those end up canceling. Outer and inner cancel. And then I'm left with last negative 5 times a 5, negative 25. Over, now here's the deal. It's going to be very tempting to sort of do the same thing we did here, where you take this x and you distribute it through. But you do not want to do that in these problems. This x is my problem. It's the thing that is not letting me do this direct substitution. So my goal is to be able to get rid of it. I don't want to get it buried by distributing it through. Leave it out in front and don't do anything to the denominator. Okay, so now I've kind of rewritten it. Now let's see if there's any reducing that can happen. This 25 and this negative 25 are going to cancel. And we got lucky here. This x now is sitting by itself, so it is fair game to reduce with this x that's being multiplied. Okay, and then I think that's it. One thing to note is you cannot like square root this 25 and call it a 5. It's the square root of this quantity, and you cannot do that square root unless you've already added these together, and we can't really add them together. So don't square root that 25. Here's what I've got left. I've got nothing left on top, so I'm going to put a 1 over the square root of 25 plus x, and then outside of that radical, make sure that's obviously outside of the radical, I got a plus 5. Once you do your simplifying, that's when you go back to that direct substitution and see if it'll work. If you plug in a 0 right here, that's just going to become a square root of 25, which is nice. Square root of 25 is 5 plus 5. I'm going to end up with a 1/10 on that. All right, I'm kind of just doing one of each type here. So if you get stumped on one, feel like you need to watch that again to see that play out, that's fine. I'm going to do one more type. It's a piecewise function. If your limit is approaching a value where the piecewise function changes, that means that right here, my limit is approaching 2. And 2 is the exact spot where we're switching from one function to the other function. So if that's the case, you're going to check the left and right limits to see if they're equal. So let's give that a shot. So I'm using this function anytime x is less than 2. So that would be on the left side of the function. So I'm approaching 2 from the left. So really, that would be my problem down here, approaching 2 from the left. So let's plug 2 in. 2 squared is 4 plus 5. That's a 9. Okie doke. And then the second function I am using anytime x is bigger than 2. So that's going to be on the right side. So that means I am approaching 2 from the right because that's the function happening over on the right side. So let's plug 2 in here. That's going to be a 2 cubed. That's 8 plus 1. Got 9. All right. They are equal to one another. So if they are equal, then you found the limit because you're coming in from the left and from the right and you're getting the same answer. In that case, you're getting it to equal, the limit would be 9 in this case. Now, if they're not equal, then your limit does not exist. Do you remember from yesterday, what would be the reasoning on that, do you think? Okay, it is typically because it is approaching different values. And that's because these piecewise functions are the ones that usually have some sort of a jump. They go from one to some other function. And there's, because the graph, I'm going to say, often has a jump in it. Oops, in it. Okay. All right, now actually, look at this function one more time. This right here is our piecewise function. I actually wanted to show you what that looks like graphically. So here's what we've got. This piece right here is a parabola that's been moved up 5. That's this green function right here. But I only graph it when x is less than 2. So you can see when x is 2, I stopped graphing it. All right, now the second function is an x cubed plus 1. And that's just a cubic. That's kind of like that snake graph. And it's just gone up 1, only looking at the right side of this graph. So ultimately, here's what that graph looks like. It, instead of crossing at the origin, it's going to cross here at 1, and it's going to come up and do this, and then go way up. And what all I'm really seeing is this piece here. It almost looks like it's linear after a while. Now, I'm going to go ahead and erase that back off so it doesn't clutter up our graph, but that's what's going on. Now you can see on the previous slide when we were approaching 2, you can see at x equals 2 right here, x is equal to 2, right here is the spot where you switch from one to the other. And do you notice that right here, you're at 9? Yep, that's what the y value was approaching, was 9. Now, I'm going to change this up on us and say what happens as x approaches 1. Well, 1 is not the spot where the function is switching. So because of that, it's actually continuous at that spot, and you would just do direct substitution. Now, this is an example of a piecewise function where these two parts meet. I feel like it's the first one I've done where they meet like that. A lot of times our piecewise functions might have some sort of a jump kind of thing in them where maybe you have this parabola, but it doesn't conveniently meet there, and then you got some kind of a line or something, and there's some sort of a jump. That would be discontinuous at this spot right here, between there and there. If the two functions meet, then when you do the direct substitution, you're going to end up getting the same number like we did on that previous one. Okay, now, again, this particular slide is really about how do you approach it if you're approaching a number that is not the special point where they swap functions. If that's the case, then you only plug it into the appropriate function. So if I want to plug it into 1, well, since 1 is less than 2, I want to be using this top function, not this one down here. And so when you put 1 into this, you'd get a 1 plus 5, so that limit would equal 6. And so you can see over here, as x is 1, 1 comes up to here. Yep, that y value is a 6. You would not be getting the same thing if you plugged into the second one. See how that would only get you a 2, because you would be using the wrong function. And at that spot, they're not matched up. Okay, all right. I hope you understand all of this pretty well. Go ahead and give it a shot. You have day 2 limits worksheet is the homework for this. Good luck.